Hello, everybody. Welcome to this session of the seminar on application of topology and geometry. I'm pleased to introduce our speaker today, Eric Goubault. Eric is professor of the computer science department of École Polytechnique in France, where he's the current head of the department. And as for research, Eric is interested in verification of numerical programs systems and geometric methods for concurrency, and directed topology and applications to verification of concurrent and distributed systems. Eric is one of the pioneers in this topic, and together with others, he has written a book, probably the book on the topic. And today, Eric will talk about directed topology complexity. And so please, Eric, go ahead.
Okay, thanks a lot. Thank you, Armando. Thank you for the nice introduction, and thank you to everybody to be here. So I'm going to talk about some recent work with Michael Farber and Aurélien Sagnier about complexity in topology, and more precisely, topological complexity in directed topology. So there's already some classical work on topological complexity in classical topology. I'm going to recap briefly. I'll show some of the motivations of the work and why we wanted to generalize this to a directed framework. So the overall context is that of robotics. I mean, the applications you have in mind when you look at topological complexity is really about robotics. So imagine you want to design motion planning algorithms, which are very important in robotics. So algorithms which would, given a pair of start point A and end point B, tell this little robot how to get from A to B. As you see, you may have many solutions. This is a continuous path here, actually, but it's a bit wiggly. I mean, it wiggles around the pillar here, and maybe it's a bad choice. I don't know. Maybe there are some less complex choices. And the idea is really to discuss about the complexity of such motion planning algorithms, meaning that you may have some very simple, meaning continuous rules, continuous in A, B, for some subspace of pair of points A and B. And maybe when you leave this subspace of pair of points A and B, you might have to give another rule to have the robot going from A to B. So for instance, here, A is very close to B. You might have thought to go directly from A to B, whereas if you are far apart and next to the pillar, you might want to choose to go around and behind the pillar. It's probably two different rules, going left and right of the pillar, and certainly there'll be a discontinuity when sort of getting from one rule to the other. So it's a minimal number of rules you need to give the robot to go from all A's to all B's. That is going to be the complexity of such motion planning algorithms. So I'm going to define that shortly. This has all been introduced, for instance, in Michael Farber's classical book. And it's really something very deeply rooted in the topology of the configuration space of the robotic system. And as you will see, the underlying assumption in classical topological complexity is that you can move back and forth. You have no specific preferred direction. You can go back to your previous steps. You can move an arm forward and backward. So it's really an undirected problem at first. So let me formalize this mathematically, as is done in the classical work on topological complexity. So you have to consider first what is well known, the path vibration map, which associates to each continuous path its pair of endpoints, its pair of start and end points. This is a self-vibration. This is not only a continuous map, it has very interesting topological properties. And abstractly, trying to find a continuous, a motion planning algorithm is trying to find a section of this vibration map. That is, of course, you want to find, given any pair of points A, B, some continuous map going from A to B. So this is precisely the definition of a section of this path vibration map. And now, as I told you, you are going to measure how far from a continuous section you are going to be. So that's going to be the complexity. So the definition is as follows. The classical topological complexity of a topological space X is going to be the minimum number n of partitions of X cross X into n, so technically Euclidean neighborhood retracts, F1 to Fn, such that on each of these different Fi's that partition X times X, you are going to have a local to Fi, a local continuous section to the path vibration map. So you're going to try to stretch out as much as possible the partitions to get as more continuous maps that will give you a section of the path vibration map. So that's actually just the abstract version of my little drawing I had in the first slide. This is the pillar you want to not go into. I mean, an A and B are the start and end points of my little robot. And so you have to make choice whether to go behind or in front of the pillar. And as we will see later on, there's no way to go continuously from all A's to all B's. There's no single continuous rule from all A, B's on that annulus to give you a continuous motion planning algorithm. So the topological complexity will not be 1, it will actually be 2. You will have a partition into 2 subspace of the product space here, so that you'll have a continuous rule for one part and another one for the other part. And actually it's pretty simple to see that it cannot have complexity 1, because you can prove very easily that having topological complexity being equal to 1 is equivalent to being contractible as a space. And it's very easy to see. If you have such a continuous map from the product, the product of X with itself into the path space, which is a continuous section of the path vibration map, then just choose some point x0 in X, then you're going to have S of anything, comma, x0 being a contraction, a continuous contraction or retraction onto x0 of the whole space X. So this section, if you freeze x0 here as a second argument, is going to give you a continuous deformation from X to the point x0. So this is a contracting homotopy. So certainly it's not contractible, so certainly the complexity cannot be 1. So as you see, what is very interesting, of course, as well for me in directed topology, the generalization I'm going to sketch, is that topological complexity is also a nice invariant of homotopy equivalent, as we will recap. And so it's a good sort of litmus test for directed topology. If we have a good notion of directed topological complexity, then we can test that our homotopy or dihomotopy equivalencies are going to be interesting. Okay, so before getting to that, let me motivate why one would like to go from classical topological complexity to directed topological complexity. So when you are really interested in real control systems, so systems like my robot, which are governed by some ODE in general, which is dx over dt is a function of x of t, of the state and of the time, but also of controls that you're giving on the robot. You tell him to turn the wheels left or to accelerate or things like that. That's the sort of controls I have on my robot. Then physically speaking, I mean, U has many constraints. I mean, you cannot accelerate more than some physical quantity in a given architecture of your robot. You cannot turn the wheels up to some angle, after some angle. You cannot turn them in a faster manner than some constraints, some physical constraints are enforcing on your physical apparatus. So U of t is bounded. So what it means is that when you're looking at all possible paths that the robot can follow, they can only be paths that agree with differential inclusion, actually. If you take all constraints on U and its gradients as well, you are going to say that the evolution in time of your state of your robot is going to belong to some set f of the current state, x of t, and of time. So that's a differential inclusion. And you should think of it as, in general, prescribing some sort of cone in the tangent space into which you can evolve. I mean, you see these green cones attached to each point in the tangent space. You can only evolve within this cone. You cannot go that way or back. You have to follow some of these constraints. Okay, so I'm not going to explain the whole motivation. Ultimately, we want also to use the directed topological complexity to measure the complexity gap between several methods in optimal control. You have local methods to find optimal controls, like Portray-Yagin maximum principle, or global one, Hamilton, Jacobi, Bellman. And we believe that it's really due to the underlying geometry of your space that you can measure the difference of complexity of these methods actually in optimal control. I won't go into that. It's not done yet first, and then it's pretty complicated. The second motivation to go to directed topological complexity is that contrary really to classical topology, there are many ideas about what should be dihomotopy equivalencies, but I mean, we have competing definitions really, and so it's good to have some good sort of test cases so that we can decide which one for us is sort of better, is the one which is going to be the definitive, let's say, dihomotopy equivalence. I also will not speak today really about applications to concurrency and distributed system theory, which actually has begun the field of directed algebraic topology. First, because that makes a slightly different talk as my favorite talks in general, but also because it's more natural to introduce that after the work of concurrent systems. But let me just mention that in concurrency, sections of this map just correspond to schedulers. Let's say you have two states in your system, and what you're asking is how to schedule my sets of processes so that you can reach the beginning state of your automaton, let's say your concurrent automaton, and you can reach the final state from this beginning state. So these sections, they have meaning. Motion planning is just scheduling in that context. Okay, so now let's go to more formal mathematics. So the context in which I'm going to define this directed topological invariant is the one of directed spaces introduced by Marco Grandis. There are also other models we've been introducing, but this is pretty convenient here. So a directed topological space is just a topological space X together with a subtopological space of the space of continuous paths, which are going to be called directed paths. You just extract from the set of continuous space of continuous paths. You just extract the paths you want to declare as directed paths, and axiomatically, you just want to ensure that such sub space of directed paths contain at least all constant maps, all constant paths. Let's say paths which stay on points. You want concatenation, of course, and you want also it to be close in the composition with reparameterization, so continuous and non-decreasing maps from the unit interval to the unit interval. And that's the very basic axioms you might want to enforce to get good enough directed spaces. And so all things such as these pictures I won't explain today, are particular directed paths which come from concurrency theory and which you can study pretty much. I'm going to concentrate on the differential kind of framework, differential inclusions, and I will argue very quickly that, I will claim very quickly, let's say, that if you consider differential inclusions and solutions of differential inclusions, under some conditions on this capital F, which is a set map from Rn to subsets of Rn, under some simple conditions and some classical conditions, you are going to define a display structure on Rn. And so we are going to go into the realm of directed topology. So I won't give you all the details. You just need to ensure that the map F has enough structure so that you have local solutions to the differential inclusions. So these are parts of and you have local solutions to the differential inclusions. Typically, this map F can be the closed convex hull of continuous Lipschitz functions. So you are really in that situation, which is on that picture. That is, you have the convex hull of two continuous flows on X, and you are considering all possible trajectories within the closed cone delimited by these two vector fields, the upper one and the lower one. And in that case, as you have local solutions, you can define the directed space structure as being, the directed paths as being just concatenations of local solution of this differential inclusion, modulo reparameterizations, because you need to be close in the reparameterization. So that's about it. And now I have also to define what is going to be its directed topological complexity. So now I have my Px is the set or the topological space of directed paths, and I'm going to associate to directed paths the pair of endpoints, start and end points. So it's going to be included in x times x, except I'm not going in general to be surjective. So the first thing I have to sort of get away from my path into my discussion on directed complexity is that this map is in general not surjective, so I want to make it surjective. So I will consider it to be in value into that gamma x, which is a set of pairs of reachable points within x cross x. Otherwise, it has no meaning to ask ourselves whether I have a section from x cross x to px, of course, because sometimes I have pairs of unreachable points, so I have no path at all. So I need to restrict the codomain, the range of my dipath space map to that gamma x. And now I can define similarly to the classical case the directed topological complexity, so TC with this arrow on top of it, of the space x, as again the minimal number n, such that now it's gamma x, not x cross x, such that gamma x can be partitioned into n sets, so n Euclidean neighborhood retrials. And so such that I can find locally to each fi in that partition a continuous section into the directed path space. So of course this will solve my motion planning under constraint problem, because my constraints are encoded into that space of directed paths. Okay, so there are some generalizations you might want to study later on. I won't speak about them today. You can be interested in swarms of robots, distributed systems of robots, and you might want to see whether it's complicated to make them gather to a unique point. And in that case, you want to replace Px by some other exponential of two topological spaces, let's say. So you want to replace it by x power k, k being some sort of confluence of many different directed arrows. And if you think about what you're going to study as sections of Px into some subspace of here 3 copies of X, it's just that 4 copies of X because you have W, so you have to take into account. You want to see a section is going to encode the fact that you want to make these 3 robots, 1, 2, and 3, gather onto a unique point W. Okay, so you can also ask yourself, is it complex to make gather a certain number of robots together? And it's going to be a topological problem again. More classically, there's a higher topological complexity, so you can also look at X, at the continuous paths on X, but then look at different waypoints, let's say, at different points through which you want to get in your path. So instead of looking at the path space vibration onto X cross X, you're looking at vibration mapping the space of maps, the space of paths, onto a certain number of copies of X, where you want to impose to go through different intermediary points, or which are called waypoints in motion planning. So you want to go into, for instance, each room of this building and want to see how complex it can be. I won't discuss about that, but there are some directed analogs to that. So before stopping for a few first questions, I want to show you that already the definition is a bit different than in the classical case, because in the classical case, this particular n, which is going to be the topological complexity, you can define it in many different ways. You can say it's a minimal number of partitions into Euclidean neighborhood retracts that will partition the X cross X, X times X. Or you can say also the minimum number of open subsets that will cover X times X, or the minimal number of closed sets which will cover X cross X. But here, as you've seen, I've only given the definition with a partition into E and half, and there's a good reason to that, because there's no way you can have the same things with coverings by open sets. So just look at this example, the directed circle, let's say. So it's O1. So just it's just 2 segments glued together onto B and E, and the 2 segments are oriented the same way from B to E. So if you had a covering C by open sets of the pairs of reachable points of this directed space, such that there would exist a continuous section of the dipath map on each open set, then you would certainly have an open set in that covering C. So this open set, I call it O, which will contain BE. And if I have such an open set O, then I'm sure I have a product of some small open neighborhood of B on my space, which I call U, times some small neighborhood of this space, which I call V, which is the intersection of the blue thing with my space, of course, around E, which will be included in O. And then, actually, this is just impossible to find a continuous section on such U times V open subsets of my space gamma O1, because, for instance, if I'm on B, if I want to go from B to E, and I've chosen my section to go through the upper arc, then if I'm looking at just something very close to B within U, I'm still trying to reach E from there, but I'm looking at a point which is actually on the lower edge, on the lower arc. I mean, there's no way I can choose this upper arc to go, because it's just unreachable from this close enough point below just unreachable to go to the arc above. So I'll be going to have a discontinuity of choice because below I have really to choose the arc below. I mean, these points next to B within U and below here where you see my mouse, I need to choose the lower arc. And so it's not going to be a continuous choice because I've chosen to take the upper arc from B to E. And there's no way you can get around from this. So there's no way to define a covering by open subsets with continuous sections that will be giving you anything in such spaces. So that's why we choose ENRs, and that's going to be a good definition. You can see that a bit differently, a bit more abstractly. The fact is, in the classical case, the map from the path space to the pair of endpoints is a fibration. But in our case, if you go from directed path to gamma of X, the pair of reachable points, it's not going to be a fibration. If you look at the inverse image of BE with respect to chi, it's going to be homotopy equivalent to S0 to two copies of points. You may have two distinct die-paths from B to E, whereas the inverse image of all other pair of points within the space of reachable points, gamma O1, just going to be a homotopy equivalent to 1 point. Actually, it's just going to be 1 point, essentially. So it's not going to be a fibration, and then the definitions are not going to work the same way. Okay, so let me just, before stopping very quickly, let me just state now that these are going to be essentially different quantities. The definition looks the same. It's not exactly the same already. This is going to give essentially different quantities, except in some cases. Let me just give you one example before stopping for a few minutes. Look at this non-trivial graph. So you have, it's a directed graph, it's a directed space. You're going this edge up and right, this edge down and right, but these two other edges are going down left and up left. So they're meeting together, let's say, onto these 2 points. If you think about motion planning, which will agree with the directions of these arcs, then the directed topological complexity is going to be 1 because you can take any pair of points in the pair of reachable states. There's just one directed path anyway up to reparameterization. From green to red, you can take any pair of green to red anyway. There's no way to start from there and finish there because it's in the wrong direction. So you're always within one arc which is directed. So you just have one die path essentially from one green point to one red point. So it's going to be a continuous choice, simple choice. Directed complexity is going to be 1. But then, as a topological space, this is just S1. If you forget about direction, S1 is not contractible, of course. So the classical topological complexity, as I told you before, it cannot be 1 because it's equivalent to have topological complexity of 1 and being contractible. So certainly, as a classical topological space, the classical topological complexity is not going to be 1. Actually, it's going to be 2. I'll recap that later. So they're not going to be equal quantity. Okay, so let me maybe stop quickly here if there are any questions about the definition and the first the observations you can make, and then I'll show you the results we have on that. Is that clear for everybody? Otherwise, I will proceed on showing you actually some cases in which you can compare these two notions. So, the easy thing is when we have what we call strongly connected directed spaces. So it's just a generalization of strongly connected graphs. So you say that directed space X is strongly connected if you can, for every pair of points in X cross X, XY, you can find a directed path from X to Y and a directed path from Y to X. So this means that gamma X is equal to the Cartesian product of X cross X. And of course now, if you have a partition of gamma x into which you have local continuous sections that give you an directed path for each pair of points A, B in x cross x. Then in particular, for each pair of points A, B in x cross x, you have a continuous section into the space of just paths, not even directed ones, because directed paths are in particular undirected paths. So you have got a partition of x cross x with local sections of the path vibration map. So of course, you have this inequality in that case. The classical topological complexity of x is going to be less or equal than the directed topological complexity of x. Now, the contrary is not obvious. You may not have equalities, but at least you have that. So, for instance, if you look at S1 directed, and that's just the undirected S1, but where you choose to circle, you choose a directed structure which is different from my O1 I had before, where you can really turn around in the same direction. Then it's strongly connected, of course, because for each pair of points, you can go one way or the other way. So it's going to be strongly connected. The ordinary topological complexity is 2. It's not 1 because it's not contractible, and it's 2. It's easy to see. I'll show you that later if you want. So we are sure that the directed topological complexity of S1 is less or equal than, actually, that's contrary. It's greater or equal than 2. Okay. So now there's another simple case in which you can compare things a bit more contrived way. Initial points in your directed space. An initial point in directed space, just some distinguished point x0, such that you always have a means, a directed path, a means to go from x0 to all x in x. And in that case, you can prove that under some minor assumption, which I don't detail here, the classical topological complexity of x is going to be less than 2 times the directed topological complexity of x minus 1. So this can be, I won't give you the whole proof, but you can see that because what you're going to do is, so as you know that you can always get from x0 to any x with a directed path, so you're going to give a way to go from any x to any y in x cross x by going from x to x0 by the inverse directed path you're going to have through your partition of gamma x through the characterization of directed topological complexity, and then compose it with a directed path going from x0 to y. And so if you are able to partition in k equal to 4 in that picture, in k parts gamma x, k is the directed topological complexity, then you are going very easily to find at least a way, a partition of k square subsets of x cross x for with continuous sections into the topological space of this. But actually you can do better, because under this slight, very classical assumption on the topological space X, you can regroup some of these k-square parts, because actually if you take sufficiently distinct parts in the products, then they're going to be completely separate choices. So you can actually regroup parts of this k-square partition I've been giving you, which is just the fi times the fj by this formula. And you can check you will have just 2k-1 such sets. And this means that you can partition X cross X by at most 2k-1 subsets on which you will find a continuous section of the path vibration map. So this is what gives you this inequality. This is a bit technical, I mean the regularity thing, but it's feasible to see that. So you have a means to compare topological complexity under some basic assumption. Now I'm going to sketch the results we have from the lower dimensional spaces, that is graphs, interesting spaces, let's say graphs, to higher dimensional spaces. And you'll see it's not obvious. We don't have tons of results. It's not easy. And even for graphs, we have to work a little bit. So in classical topology, it's easy to find the topological complexity of graphs. You have three cases. This is the Betti number, the first Betti number of G. So actually, all graphs are homotopy equivalent to a bouquet of circles, a bouquet of B1 of G circles. And what the classical topological complexity sees of graphs, I remind you, it's homotopy invariant. It's an invariant of homotopy equivalence. Just can distinguish 0 bouquet of circles, 1 and 2, and the rest is just the same for when it comes to classical topological complexity. So when the graph is contractible, so G is a point, and basically homotopy equivalent to a point, and then the classical topological complexity is 1. When there's just one cycle, then when it's mostly S1, the classical topological complexity is going to be 2. And when you have at least 2 in the, actually at least, I should have put greater or equal than 2, at least 2 independent cycles, then the classical topological complexity is going to be 3. If the Betti number, the first Betti number is greater than 2, the topological complexity is going to be 3 again. So that it's not going to work the same way. Look at this graph, 3 edges. You have 2 independent cycles, Betti number is 2. So actually the classical topological complexity of this graph is going to be 3. Whereas you can easily find, if the arcs are going all from left to right, you can easily find partition into 2 subsets of the space of pairs of reachable points, on which you will be able to define continuous sections to the direct path space map. So the first partition is just, there's a typo here, it's just the pair of endpoints, BE, it should read BE here, and the rest is just the complement, of course, it's a partition. Just meaning that, of course, when you are in the interior of the 3 arcs, then you have no choice. I mean, you just have basically one dipath from one point to any reachable point from there. So there's a continuous section, of course, on the interior of these 3 arcs. And then the only thing on which you are going to have to make a choice is from the beginning to end state. You have to make a choice whether it's the up arc, the middle arc, or the down arc. So the directed topological complexity is going to be 2, so it's strictly less than 3, the classical topological complexity. Okay, so let's give some more examples now of graphs, and let's give some theorem about graphs. I get back to this other version of S1, the classical S1, where I orient things so from left to right. It's not the S1 I had before, where I could loop around. So it's easy to see that the directed topological complexity is not going to be equal to 1. I don't give you the argument. You can actually use the fact that my previous statement that O1 has an initial point, which is the left point, which is the point 0. And you can use the fact that the classical topological complexity of this space is 2. And as you know, for directed spaces with an initial point, you have this inequality. Directed complexity is less than 2. No, sorry. Classical topological complexity is less than 2 direct times the topological complexity minus 1. So as it's 2, you have 2 TC, 2 times the directed topological complexity minus 1 is greater than 2. So it's going to be strictly greater than 1, and the directed topological complexity. You could find some other arguments, but at least you can use that one. And now you can prove it's less or equal than 2 by giving a suitable partition of the space of reachable pairs of points. There again, it's easy. You just look at the interior of the 2 arcs, and any pair of reachable points is like these pairs of green and red points. And there's essentially one directed path from green to red, so there's a continuous section which you can find easily. You have no choice. The only choice you have to make is from beginning to end point, and you can choose whatever you want. So this is one partition of the pair of reachable points, which is just beginning and end, and the other partition is all reachable points within the interior of these 2 arcs. And this gives a partition to 2 subsets of the reachable pairs of states, on which you can define a continuous section. So you just proved that the directed topological complexity is 2 for that space. For S1, directed S1, where you can turn around, you've chosen to revert the back edge, the down edge. There again, the directed topological complexity is 2. You can find a partition of the pair of reachable points where when you are on the diagonal of x cross x, you just take the constant die path. When the green and red states, the beginning and the end states are equal, you just take a constant path. And where they're not equal, then you just take the shortest path from green to red. And that's going to give a continuous section to the dice space, the dice path space map. We can show also it's not equal to 1, so the directed TC is going to be 2. And we can actually show, more generally speaking, that as for classical topological complexity, there is a bound on the directed topological complexity of directed graphs, and it's going to be the same bound, it's going to be 3. I won't give you the full proof, but the partition is there. It's just, you can just take as first partition the sets of reachable vertices in your graph. Then for the second partition, it's going to be pairs composed of a vertex and something which is in the interior of an edge. And the last partition will be the pairs of reachable points from the interior of an edge to the interior of another edge. And you can check, it's the same actually partition you're using for classical topological complexity. You can check that it's going to partition, you're going to have continuous sections with directed paths using this partition. So you're going to give this upper bound very easily. But in general, as we've seen already, it has the same bound, but it's not equal to the classical topological complexity of graphs, except in the case when the graph is strongly connected. So remember, when we have strongly connected directed spaces, we have an inequality between the classical topological complexity and the directed topological complexity. The directed topological complexity is greater than the classical topological complexity. But here we know it's actually exactly equal to the topological complexity of the graph when it's strongly connected. And it's going to be the formula I gave before, so it's a minimum of the Betti number, the first Betti number of the graph, and 2 plus 1. This can be seen easily. I won't give you the proof. So at least in that case, we know exactly the directed topological complexity of graphs. We don't know exactly, apart from that bound, the directed topological complexity of any arbitrary, not strongly connected directed graphs. Of course, it relates to the topological sort of the graph. the decomposition of graphs through its strongly connected component, but it's not easy to find a formula. Now I'm going to go to higher dimensions, and going to give you some results we have, which are actually very similar to the classical results we have in classical topological complexity. So first of all, you should remark that there's the category of this space is complete and co-complete. You have at least binary products. So it's just the binary product of the underlying topological space and of the topological spaces of directed paths. And similarly to the classical case, for regular spaces, once again, it's a minor technicality which I won't go into. You have this inequality. The directed topological complexity of the product space x times y is less or equal than the sum of the topological complexities of x and y minus 1. And that's exactly the same proof as in classical topological complexity. I won't give it to you, it's right there. You just look at all products of each part of each partitions you have, one for x and one for y, and then the regularity assumptions you can regroup, as I did before actually, you can regroup some of these products of these two partitions into just this number of parts, and that's going to prove to you this inequality. So that's the same as for classical topological complexity, and right away we can give some bounds on some applications to some high dimensional directed spaces. So you have two versions of an n-tori here. On the left you have a version which is the n this O1 power n, so n copies of O1 multiplied together. So O1, remind you, it's the one in which you go in the same direction onto the two hemispheres of S1, go from left to right. And in that case, as O1 as an initial point, you can use the inequality I had, and I know that the classical topological complexity of the n-tori is n plus 1. So I can use this as a lower bound to my directed topological complexity. And I can use also my other bound, which is that one, the fact that it's product space, to get this upper bound, which is n plus 1, because I know that O1 has directed topological complexity of 2. When I do the power n, I know it will be at most n plus 1. But I don't know exactly what is the directed topological complexity of this version of the n-tori. Whereas I know that for this other version, where I look at the n times product of S1, so the version of the d-space of S1 in which you can go around in the directed path space, then I know that in the product it's still going to be strongly directed. And with the fact that the classical topological complexity of S1, the underlying S1n, the underlying n-tori, as I know it's n plus 1, using strong directedness, I know that the directed topological complexity of this version of the n-tori is going to be greater or equal than n plus 1. And now, using again this inequality I've just proven, as I know that the directed topological complexity of the directed S1 is 2, I know having n copies of the directed S1, the directed topological complexity of this n-tori is going to be less or equal than plus 1. So now I have the two sides inequalities. I know it's going to be n plus 1. So I'd like to know this directed topological complexity, because this n-tori as a directed space is essentially different. It's not a dihomotopy equivalent to this version of the n-tori. I'd like to know whether you can distinguish already this through the directed topological complexity invariant somehow. or not, but right now we don't know that. Okay, so more generally speaking, for higher spaces, it's a bit more complicated than the classical case. In the classical case, for a cellular complex, we know the classical topological complexity is going to be 2 times the dimension, the largest dimension of the cells plus 1. It's not going to be true for general directed spaces, but if you restrict them to a suitable class of complexes, of geometric cubical complexes, we believe, at least not fully written down, that we're going to have the same inequality for the directed topological complexity. But for some crazy directed spaces, not going to hold. You may be fairly high up than this bound using the dimension. Okay, and now I want to finish on some of the results we have on directed complexity on some case which took us quite a long time and which has been solved independently by other people, by Mark Grant and collaborators, which has been very intriguing to us actually. So it's a case of more general directed spheres than S1 O1, let's say, I had before, which is the version I'm interested in. So we know everything about the topological complexity of classical spheres Sn in the classical case. We know that it's 2 if n is odd. We know it's 3 if n is even. I don't give you the proof, the classical proof, it's there. We did claim many things about this version of the directed sphere in dimension n. So this version is a generalization of O1, let's say I had. So we just see this directed sphere as, well, up to deformation, an hypercube of dimension n. So actually the boundary of an hypercube of dimension n, in which the directed path structure is given by the partially ordered structure you have in the ambient Rn. So let me explain that. Let me just see this hypercube I have here, or this cube here, as the product of 3 directed segments. So this one times this one times this one. And the directed structure is given by saying that directed paths are like these green and blue paths. They are going to be the continuous paths that are increasing when you look at the projection on each of the 3 coordinates on each of the 3 segments. So you want to follow the direction given by the 3 directed segments you took the product of, and you want to increase the 3 coordinates. And now I'm saying I want to study the directed structure on the faces of this hypercube, on the boundary of this hypercube, which I call the directed sphere of dimension n. Okay, and actually the surprising result is that the directed topological complexity of On, this sphere of dimension n, directed sphere of dimension n, is always 2. I had for O1, I knew it was 2. I could show you a partition into 2 parts, but it's actually true for all n's. You don't have to distinguish between odd or even cases, whatever. That's been proven by Grant and Borat. And I won't give you the partition. We had actually for some time another partition than theirs, but the principle is that somehow you can sort of find, you can decompose this directed Sn into 2 parts. One in which, for each pair of reachable points, we will always correct the coordinate of the start point, the green point, to get to the coordinates of the red points in some order. So here you choose to correct first the y coordinate, then the z coordinate, then the x coordinate. But you cannot reach all pair of points that way by correcting first the y coordinate, then the x, and the z coordinate. You have to find another part in your partition in which you will decide of some other order to correct the coordinates to go from green to red. This other order might be to correct first the z coordinate, then the y coordinate, then the x coordinate. And so they have a slightly different motion planner and partition in the paper that's going to appear, I think, in the Journal of Applied and Computational Topology this year, which has been presented also in GETCO last year in Oaxaca. But this is a principle. You can find some motion planner giving some order on the coordinates you want to correct. That's quite fascinating, really, as a fact. Okay, so now I will just finish by some observations about what it teaches us, this topological, directed topological complexity, in the sense that we want to study directed spaces up to some sort of dihomotopy equivalence, and we want to have this directed topological complexity to be an invariant under dihomotopy equivalence. And in fact, many of the definitions we have of dihomotopy equivalence will have directed topological complexity as invariants, and I would rather say that the ones which do not agree with directed topological complexity are not good enough. Because it's, I mean, even for application purposes, this is, and in terms of topology, this is a very natural thing to ask. That is, that directed topological complexity is an invariant of a good dihomotopy equivalence. So I'll just be very quick on that, but the fact is we have a counterpart of the fact that a space which has topological complexity of 1 is contractible. So we have this because when we have the directed topological complexity of a space X, when it's equal to 1, this has strong implications on what the directed path space look like for each pair of points xy in gamma x. You can very easily see that if you have this directed topological complexity is equal to 1, then it means that you have a global section from gamma x to the space of directed path on x. So it's going to be a global section of this map which gives you the endpoints on each directed path. So if you have such a continuous section, then you go from A to B in black here to actually to S of AB, S being that section, that continuous section, because you can just at time 0 take the full black path. At time epsilon you'll take actually it's the contrary here, sorry. At time 0 you'll take the whole green directed path S of AB. At time epsilon you'll take mostly S of A P of 1 minus epsilon, and then you'll glue this with the rest of P, the rest of the black path, and then at the time 1 you'll end up with having just the black directed path. Okay, so you're going to use partly less and less of S of AB, and then concatenate with the rest of your path P in black to give a deformation from the red path, directed path, which is S of AB, onto P, which is any directed path from AB. And this is the sort of minimal requirement, let's say. I mean, I would have to be a bit more technical here. to define directed contractibility. There's a bit more to that. There's a continuity condition on the pair AB, linking AB to this homotopy on the path space. But basically, yes, this is a contractible, a dicontractible space, and we will have a theorem like in ordinary topological complexity, stating that and there's a good enough notion of dicontractibility, which I try to show you here on that picture, which implies at least that all path spaces are contractible. Then dicontractibility is equivalent to the fact that the directed topological complexity is equal to 1. Then we have also some links to some homological invariants we have been introducing on directed spaces, which we call natural homology, and which actually measure, let me show you that, yeah, I don't have it here, measure the different homotopy types you can find among the directed path space on a directed topological space X. So for instance, this is O1 again, so two arcs going from 0 to 1, and the different path space you might find when you make X and Y vary, the endpoints vary, can be either a path space which is homotopy equivalent to a point, because you are in the interior of an edge and you just have basically one dipath from X to Y, or the only other homotopy type of path space you can encounter for this directed space is a path space from 0 to 1, which is homotopy equivalent to 2 points. The one which describes all paths from 0 to 1, which goes up, and the other point is the ones, it's the point B here, the ones which go below. So you have two different homotopy types of path space onto that directed space, and the natural homology actually exhibits the fact that there are two different homotopy types, and when you have two different homotopy types, when all directed spaces, when all directed path spaces are not contractible, then you're not dicontractible, then you have a more complex topological complexity. And we have some hints about how to relate these constructions, this rather complicated construction I won't show today, which tells you all about the variations of, that's a bit like persistence homology in some ways, shows you all the variations of the topology of the directed path space when you make X and Y, when you make the endpoints vary. We have some hints about how to relate that to the directed topological complexity. So we have also a minimal dihomotopy equivalence notion, which is shared by some different definitions of dihomotopy equivalence, which basically tells you that you have to have all path spaces being homotopy equivalent between the two spaces X and Y. And so under this basic dihomotopy equivalence notion, we can show that actually this notion of directed topological complexity is an invariant of this directed homotopy equivalence. So this sort of close the loop of this talk. We have a reasonable notion of directed topological complexity. We have a reasonable basic requirement on what dihomotopy equivalence should be, and we know at least that we have dicontractibility, which corresponds to directed topological complexity being 1, and we have that directed topological complexity is an invariant of dihomotopy equivalence. Now we have to go a bit further. So we have a good litmus test for dihomotopy equivalence. We have a good notion of dihomotopy equivalence. What we want to do is really to be able to compute more cases of directed topological complexity. I told you for some tori, we don't even know what they're going to be. For some graphs, we don't know even. And we really need to have some homological framework for dealing with these more complicated spaces. So natural homology is one possibility we're studying currently. And we'd like also to, well, have more undirected homotopy equivalence and have a full sort of model, Quillian model structure or equivalent algebraic homotopy structure, let's say, on this, which would really fill all the gaps and in which we could have all the nice theorems we have in classical topology with respect to topological complexity, with respect to some form of homology, directed homology, and these sort of things. So I'm going to stop here and answer questions. It's been partially presented in GETCO last year, as I told you. I hope it will be in the next issue of the Journal of Applied Computational Topology. Anyway, if you want to have more details, I can send you the current version we have. And now I'm ready to answer your questions. Thanks.
Yeah, I have a question.
Yeah, please go.
Yes.
Do you hear me?
Yes.
Oh, okay. I have two questions actually. The first one is about the role that homotopy groups play with the regular TC. Namely, you describe this upper bound of the topological complexity bounded from above by twice the dimension. And in the classical case of topological complexity, you can improve this upper bound by dividing by the connectivity of the space, meaning the dimension of where the first homotopy group, non-trivial homotopy group of the space appears. So I'm wondering if there is some kind of directed analog of this situation.
Yes, it's a very good question, and yes, I'm hoping we will have something similar, except we already had to struggle with the simplest inequality because somehow the problem we have, we had to restrict to some particular class of directed space because somehow, I mean, if you use the same sort of partition you get to as in classical topological complexity to get this bound, which I won't recap here, but you can almost use it for partitioning the space of except if you are not lucky, let's say, if you have a particular not so nice directed space structure, then you'll have complicated structure for reachability between pair of points in this partition that is defined on the underlying topological space. Basically, in this partition, you might be able to, for some directed spaces, to go from one point here to one point above, sideways, and also directly upwards in some directed spaces. So you might have complicated choices which make things completely non-continuous within that partition. So if you have complicated sort of non-local directed space structure in these spaces, then you are going to have difficulties finding a continuous section even within the partition given by the classical trick in classical topological complexity. But then this classical trick will work if we restrict ourselves to particular cubical complexes in which the reachability structure, the directed space structure is very nice. So already we have to struggle with this, but then I would suspect that once we have solved this, you have the sort of same sort of action of the first homotopy group, which will not be a group actually in that case, but you will have something that we can divide out later. But we have first to take care of this discrepancy in the directed world, which is due to some non-locality of the directed space, directed path structure.
Right.
Yeah.
Okay. I have a second question.
Yes.
Well, it's rather a comment. You mentioned this work of Mark Grant and Aisha Borat, where they computed the directed topological complexity of ON, which is a sphere with a particular directed topology, I suppose.
Yes, which is actually what we generally call the directed sphere, but there might be many different ones. It's actually just the boundary of an hypercube, in which you have just increasing coordinates. I mean, the directed path structure is giving by saying that you can go from one point on directed path to another if you are in the if you increase only if you increase coordinates. So locally on this cube of dimension 3, you have the 6 faces, and as a differential inclusion sort of image of things, on each point you can go in the future. The future cone will be the positive quadrant on each face. So you can really go up and right on the front face, and then on this right face you can go towards the back and up, and that's the directed structure. As you see, these are directed spaces. So it's a very particular directed structure, even by an underlying partial order, and it's actually using the fact that there's a partial order on the coordinates that allows you to sort of make a nice motion planner on 2 different parts of this space, which is going to be continuous. And that's a bit strange for some other structures, some other directed structures on the sphere. We may have very different things, but that's a very intriguing result. Yes.
Yeah, the question was if there is any kind of a reasonable alternative differential directed topology that one can put on a sphere, so that one would expect a result similar to the classical one, namely being 3.
Yes, that's a very good question again. So at some point I've been thinking of something, but I think that it needs to be thought again. So I was thinking, because I mean, in the classical case, what you're doing is for the proof that the topological complexity is 2 or 3, is that you take a particular vector field on the spheres, and so when so it's actually here. So when n is odd, you can take another vanishing vector field. When n is even, you can find a vector field which has just 1, 0. That's the only thing which makes a change between the partitions. So you can, when n is odd, you can take so not antipodal pair of points as one part of the partition, antipodal points for the other parts, and so for antipodal points you just take you just use the vector field to choose. I mean how you get from x to y in a continuous manner. Whereas when it's not antipodal, you can take the shortest path, which is going to be a continuous path. The only difference is, of course, when n is even, you have to add a third part, which is the part on which you have this vector field which vanishes, so x0, and its antipodal counterpart. So I'm thinking certainly, yes, thanks. So certainly, if you take a directed structure on the sphere, which is just given by these vector fields, I mean these vector fields, when n is odd and when n is even, they're giving a directed structure on this directed on the sphere, then I would gather that giving particular kind of structure when n is odd and n is even, then you are going to enforce that you'll have a partition into two parts when n is odd and in three when n is even. So it's of course it's a bit frustrating because we have to enforce the directed structure by saying it's given by a vector field which is never vanishing when n is odd and just vanishing in one point when n is even. But at least in that case, I think we would have the same topological and complexity in the directed and non-directed case. Now, I would suspect that there are much more general things to say. I mean, much more general directed spheres which would have the same topological complexity. But I have no good answer yet. But I would start with that sort of construction. Things get more complicated in directed topological complexity when the future cone is not one-dimensional. I mean, it is not obvious, let's say, has a topological structure. So that's the case with this directed SN, and that's not the case when the directed structure is given by just a vector field you have to follow. Of course, it's a bit cheating. You'd like to have some slack around this vector field to move around the future cone, but I don't know up to what point you can do things. Is that helping a bit? Or, yeah.
Yeah. Thank you very much, Eric.
Yeah. Thanks.
There are more questions or comments? Well, I do have a question, Eric.
Yes.
In your last slide, you mentioned, well, it says algorithmic directed topological complexity. So what exactly you mean? I mean, that was part of a future work. So what exactly you mean, like incorporating classical complexity to this?
Yes, so I'd really like to have, at least for combinatorial, it's a point just before, for mostly a cubical sort of cubical set version of things, but combinatorial directed space. The combinatorial directed spaces made up of cubical cells, let's say. So I'd like to see, yes, what's actually been done already in the simple case in classical topology. So I'd like to have this, and then if you have this, you can think that you may find combinatorial witnesses of these continuous sections, let's say, in some suitable cubical sets. And I'd very much like to see that because, I mean, we have cases in which we know how to do these things. So the case of cubical complexes with non-positive curvature. In that case, it's NPC or CAT0 spaces. In that case, in the combinatorial version of these non-positively curved spaces, you have this normal cube path, this sort of particular combinatorial path. You can make directed actually, and which exhibit continuous sections to this sort of die-path space map. And so I'm pretty sure we can, in some cases, find an algorithmic way on some cubical sets to exhibit these combinatorial counterparts of continuous sections. At least for these non-positively curved spaces, I'm pretty sure we can do that. It's actually sort of known in the robotics, sort of theoretical robotics community. That's Rob Grice in particular, who did use non-positive curvature to derive some sort of motion planner somehow. And in the combinatorial counterparts, so with Samuel Mimram here, we have a paper on some aspects of it, but we haven't got yet to this algorithmic directed TC in that case, but we're pretty sure we should be able to do something, and that would relate nicely to the concurrency case in which you have these directed spaces made up of cubical sets, and in which algorithmically you would like to show how to schedule things. Motion planning is going to be scheduling. So that would be really nice because we would be able to show how to schedule processes. What is the complexity of scheduling processes according to the shape of your concurrent processes somehow. That's about it.
Very interesting.
Yes.
Can I make just a little comment
Yes.
about Armando's question?
Yes.
This is a comment, and actually is a commercial related to having algorithmic motion planners. Nessa Mramor has some work on that, and I also have a paper on something I don't know if you're aware of. This is a paper on something that I call simplicial complexity, which is topological complexity for simplicial complexes, where what you do is a local motion planner, a local section for this vibration evaluation map, is nothing but a homotopy between the two projections, but not defining the whole space, only on a certain open set. And being a homotopy, it can be approached, if you're playing in a simplicial complex, it can be approached by simplicial maps. Namely, essentially, what you have is that you look at the two projections from x times x into x, the first and the second projection, and then deciding whether they are homotopic. It means deciding whether they are contiguous maps. You first approximate them by simplicial maps, and then want to say if these maps are contiguous or not, and then you do the same play of saying where are the local domains where you can define contiguity. And contiguity is something that is something really old and very well studied in simplicial topology. And well, there is this. I just wanted to mention that there is this simplicial version of Farber's TC for simplicial complexes.
Yeah, I'm very happy you said that because I was a bit uneasy. I didn't. I was forgetting about the actual reference, but yes, that's exactly what we're looking at. Is going from your work in simplicial TC, let's say, to maybe a cubical version, but at least a directed version of this. It's very much the inspiration of these 2 points in the talk. Yeah, very much so.
This work that I mentioned is published in the New York Journal of Mathematics. I can send you a copy of the preprint if you want.
Yeah, of course, yeah.
Okay.
More questions or comments? If there are no more questions, then thank you, Eric. It was a very nice talk, very interesting. So yeah, thanks.
Thank you.
Thank you very much.